Thank you. It's a pleasure to be here. This one. Okay, so I want to tell you about, mostly I'm going to be talking about the semiconductor industry, and sort of it's often accused of shameless scaling, but I want to give you a sense of sort of the size, and I want to also make some remarks about how, to intersect an industry that it's already established, what are the challenges that one has to overcome if one is to come in an innovation, say in the area of nanoelectronics. So I'll give you a little bit of guidance on size, the limits of scaling that we're encountering right now as we manufacture the next generation of microprocessors and memory, some of this promise of nanotechnology where it can come in, but I also want to reserve some time to talk about how we actually do R&D and how some visions of how to do innovation properly, and I think that that's a very important discussion to have in addition to looking for the next gadget or the next new thing. So, we're all aware of the power of semiconductors and electronics and what that has enabled. If we look, say, for example, at storage, this has already become cheaper than paper. And it's utilized in all sorts of devices all over the world, including the iPod and many other things that carry with us. Underneath all of the high bandwidth internet connections and so on, there's an enormous amount of sophistication in electronics and semiconductors that make this happen. And we use this continuously, as we all know, and we use services on demand and the internet and email that are very important. Portable memory applications, as we've discussed. Even displays are incorporating large amounts, obviously, of electronics, and there's discussions and talks about using organic electronics to use displays that maybe you can roll up and carry with you. There's still a little bit in the future. They're only prototypes, but hopefully in the future it can get there. And in terms of, for example, some of the things that supercomputers and high computing power, here, for example, IBM just launched sort of a product release. Before, there used to be national efforts, right? Japan would undertake, we're going to build the largest supercomputer in the world, and then the US will respond, we'll build another one bigger. Now, this is a product, I don't know exactly the cost, but maybe it's 100 million or something like that. Lots of universities are buying them. There's one in Barcelona, as a matter of fact, that got installed. So the availability of enormous amount of computing power is sort of readily there, right, underneath all these electronics, and of course, all sorts of new gadgets and new technologies. And there's a lot of focus of what's the new gadget, right? I'm not going to talk about the new gadget. I'm going to say how a large industry is intersecting and has a need to control things in the nanoscale, but I'm not going to focus on new gadgets. So microprocessors, underneath all of this, where are they? So some of these technology trends are realized in physical products, and it's this ability to shrink electronics and microprocessors and memory to ever smaller scale, and I'm going to talk about that, is what's been fueling all of this. We use over 50 microprocessors in a car today. Most of the things you buy, you might not be aware that there's a microprocessor in there, but they're mostly on embedded systems. And in the home, they're also ubiquitous. But this is a remarkable sort of slide here, which is if you're doing processing transactions, say in banking, or a credit card, or in some kind of industry like that, what the IT industry fueled by semiconductors underneath it has enabled is a performance improvement in the transactions you can process of 1% per week, which is sort of unmatched in any other area. So to the extent that there is a connection, which is very clear between productivity and the incomes that you can pay people and standard of living, this is sort of a remarkable achievement of what this can do. If we look at the cost of a car, of manufacturing, electronics pretty soon is going to compose 40% of the cost of a car. So what we've seen over 100 years, it's just an amazing improvement on the amount of computation we can do per second. Over 100 years, we have gone almost 18 orders of magnitude improvement. So $1,000 of 1900, this is the amount of computation you can do, 1 e to the minus 6. And today, right, this is where we stand, processing many, many hundreds of teraflops, right? And this upper part of the graph, that's the part that has been enabled by semiconductors. Before we did it by other means, with vacuum tubes and so on, it keeps improving. But it's an amazing number. And we continue to advance. If we look at the number of transistors, it's minimal units that switch, that allows us to do computation. There's just a switch that it's on and off. We pack today in a microprocessor, we're getting close to putting 1 billion transistors. For Europe, 1,000 million transistor. And each transistor in one of those chips, it's already smaller than a virus. Those are all interconnected, and on a single 300 millimeter wafer, which we manufacture, there might be 1,000 of those chips. And in each chip, there's 1 billion of them, all interconnected. So there is a roadmap of incorporating this in ever faster and more powerful computers. And like I mentioned, now we're releasing commercial products here that you can do 1,000 teraflops. Sort of trillions of calculations per second, and they will be available and on demand, and people will use it. So people with great ideas who can, make good use of it will make a tremendous difference. But the point here is that computing will be basically free. So this is what very often is called Moore's Law, right? What fuels this industry, which is the only metric that anybody who wants to replace something in the semiconductor industry should measure themselves against. Can you reduce the cost per function? And the cost per function is going down while everybody keeps inventing things. We keep learning at 33% per year. So again, in 25 years, we've gone, we're going to go 8 orders of magnitude of improvement. So you got to intersect a moving target that moves very fast indeed. So what do I do, and what I've learned from Hank Smith and so on? That's what we do. We're builders of this world. Well, we have. We are lithographers, and our job is to build complex structures that are aligned so that we can interconnect 1 billion transistors, and it runs efficiently. We have to have systems and chips that when we put into our mainframes or our servers, they have a mean time between fail of 17 years, right? So that's what we have to do. That's the level of performance we have to achieve. So it's very important to differentiate, and goes back to Hank's point, a research lithography tool, say these pictures is shown 1 million times of actually moving atoms and doing things like that, that will not intersect the semiconductor industry. This, you can move an atom a minute in very cold temperatures, and there's a lot of constraints there. What we're talking about is doing lithography, which Hank is going to talk much more about, this function of patterning. How do you pattern at the nanoscale? That's a crucial aspect of it. But when we want to do this is, with the resolution of today's systems, we can already do 60 nanometers, and we have a path going down to maybe 25 nanometer lines of spaces. There's a crucial difference. We want to do this we want to put down 300 billion pixels per second. And so meaning we want to process hundreds of wafers of 300 millimeters per hour. And we want to control the dimensions there to 2 nanometers, 3 nanometers, the CD control, the critical dimension control that we have to do this. So that's what's been fueling all this industry underneath, and is that the minimum dimension that we create in these transistors is been going down, as you can see here, say in the early 70s, from maybe 10,000 nanometers. Today we're here. We're 60 nanometers and still going down, basically what we're talking about. So, for example, this is what a commercial tool to build lithography, to do lithography, the semiconductor industry looks like. And this is some of the most sophisticated engineering systems ever built. Each one of these systems costs $40 million. You have to manufacture a lens that Carl Zeiss makes with absolute nanometer control. All the lenses are actuated. There's 1,000. It weighs a ton already. You have to move the wafer underneath here with nanometer control with laser interferometers, and it's moving 0.5 meter per second, while the mask that contains the circuitry that is up here moves at 2 meters per second in opposite direction, and you have to maintain that CD control, like I mentioned, to 2 or 3 nanometers, day after day, 24/7 operation. So when we look at how much does it cost, how does the industry do this? This is what the global R&D spending for the semiconductor industry is every time we migrate a node. Every time we go from, say, 90 nanometers to 65 nanometers. On the aggregate, we have to spend close to $100 billion, okay, to develop each one of these technology. So if we make claims like we're going to replace, say, electronics, you have to sum over, right, the trillions of dollars that have been invested, the tens of thousands of engineers who've worked for this over decades to replace this. So the better talk is, how do I incorporate myself into this? How do I actually add some value into you, right? That's the right way to talk about it. Wholesale replacement, I think, is very unrealistic. This is the cost of a single fab, a single production facility, and for sort of the sake of argument, comparing it to the GNP of nations. So single production facility, right, it's bigger than many small nations. And today they cost around $3.5 billion to build a new facility. And let me just show you a picture of a little video for a 300 millimeter facility in New York. And you're going a little bit inside a chip, but what you're going to see is the facility, the whole operation is handled by robots. It takes about 3 months to manufacture a microprocessor with 24/7 operations. And the whole thing is automated. We use large amounts of computer power, more than NASA uses to launch the shuttle, to just optimize and control this. These are, in each one of those wafers, there's about 1,000 chips that we were discussing. We're interconnecting 1 billion of them, and we control all of these dimensions to the nanometer. Lithography, this is where you're seeing some of the patterning. This is a planar process. We spin liquids, and we pattern them, and Hank will talk more about it. But anyway, just to give you a sense of what production looks today at that scale. So everybody has been showing this. I wanted to show it because they're our competitor. Intel has a roadmap. We also have a roadmap about doing evolutionary CMOS technology, going down to 25 nanometer. There's an enormous amount of innovation that is occurring there in the area of materials. This is the area I talked to, that we have groups that have chemists and physicists and mathematicians working together to come up with clever new things. And there's a whole host of technologies of doing, for example, it's not going to mean anything to you, but hybrid orientation technology, putting the different transistor units in different crystallographic orientations to enhance the mobility of these elements, developing novel materials like high-K metal gates so you can continue shrinking. So there's a lot of materials innovation that comes already embedded in our products so we can continue scaling. The more important thing is that we control all of these dimensions to nanometers. We have imaging techniques to see atoms as people have seen this, and this is in a production environment. You have technicians who routinely talk about, is this 2.6 nanometers, is it 1.8 nanometers? So there's a whole workforce, and there's a whole group of businessmen and executives who understand that there is a difference between your gates being 3 nanometers or 3.8 nanometers, and that has a commercial impact on how well you do in business. So that's already happened. Beyond that, 25 nanometer, the problem gets really hard. And that's why, when we require a lot of clever people thinking about ways that they can incorporate some of these ideas into a production environment. So, things that they've been discussing for carbon nanotubes, instead of using just electrons, using spin transistors, there's some ideas, maybe using photons in the future or molecular transistors. Because the challenge we have is that if we look at the frequency improvement of microprocessors over time, is that we were growing on this slope, but it's slowing down. Everybody is aware of it, that we're slowing down, and the issue has to do with power. So people coming up with ideas that address power dissipation, it's a big deal. That's what's slowing the industry down. So how you do that? So a lot of effort is put into how do we improve performance without scaling. Right? We don't scale out of sport. We scale because we want better performance. So can we do things differently? So those are the types of introduction when, say IBM led the industry in going from aluminum to copper. That improves the performance of your microprocessor, but you're not scaling, right? Or using silicon on insulator or silicon germanium, strained silicon, deforming the gates to enhance the mobility and things like that. So all of those are very important innovation that allows and fuels an industry. So again, it's this intersection of scaling down, but with cooling and, creating novel materials that you incorporate in clever ways, training silicon. It's a whole aggregate of things. So when we move from one technology to the other, we used to introduce one new technology maybe. Now we introduce 8 in a row. Altogether, it's enormously complex, and the risks that we take on that are very, very large, and it has to be first time right. So in terms of the promise, what I would say is like we have to focus below the 20 nanometer scale. That's where we have a challenge. Up to then, it's going to be very difficult, but we know how to do it. From 20 below, that's a hard problem to solve. That's what the best mind should be focusing on. Until there, I think there's a pretty clear way of how we can do things. So things like quantum computing and introduction of carbon nanotubes, I mean, that's a little farther down the road. But for example, some of the magnetic random access memory and some of the memory applications, those are very interesting things that could be shorter in time frame. I want to give you just one study when we'll be talking about self-assembly that we have people internally working on this. Let me tell you what this is about and how you could potentially use it. So self-assembly is like combination of geometry and force balancing can create a spontaneous regular pattern, and you can do these things at the nanometer scale. So if you look, and I'm going to go back to this in a second, but things like this happen in nature, right? This very complex structure that self-assemble, like snowflakes, or you can see some patterns in animal fur, or like the sand ripples. And if you look here, there is some structure that you can recognize. So the question one can ask is, if I can create this at the nanoscale, right, and this could be 20 nanometer lines of spaces, how can I use things like this to improve highly ordered structures like this that are doing lithography? So these are things we're exploring. And for example, one thing we can do is you can create minor templates and etch them and build memory devices with them. That's one of the things that has been done, and we've published with some extension. And the other one is, let's imagine you define a line. This is 600 nanometers by means of lithography. And now you spin this block copolymer on top of it. And in the right conditions, you can get it to self-assemble and form lines of spaces that in this case are 20 nanometer lines of spaces. So you do that, and then you can actually do an integration process and actually fabricate a transistor that has gain. So we've done that and built the world's first FinFET. And so this is a way that you can start exploring. I'm not saying this is going to go into production anytime soon, but it's exploration of this combination of top-down with bottom-up approaches that is really worth exploring as an example. I'd like to go back to this very important point that was discussed this morning, that in my opinion, the real reason why nanotechnology is exciting is that it provides an opportunity for people from different disciplines to work together. And I think that that is what it's absolutely key and the most interested. For the first time, I mean, we've had biologists and material scientists and physicists and chemists talking about that scale. That was nothing new. But now you have the engineers. Now you have the electrical engineers and people who build production facilities that they manufacture at that scale. And all of a sudden, that has enormous power. If we can come up with clever ideas and we can integrate it, taking advantage of the trillions of dollars that have been invested in the past in some ways, that will be very powerful. So my last set of remarks is I want to talk about the process of doing this. How do you actually do innovation today? And, and the model of the sole inventor, right? The one-man show, in their laboratory, coming out with a great invention. They go out, they get a venture capitalist, and you revolutionize. That's great. It works for certain industries. I think a discussion worth having is, does that model apply to nanotechnology? If for some cases, if you're talking about electronics, you really require billions of dollars of fabs and tens of thousands of engineers, who's going to fund that? Right? What venture capital is going to fund that? They're like, like somebody told me here, they like bits. They don't like atoms. They don't like to fund those things. It takes too long. It's too expensive. But the impact can be enormous. So how do we do this? Innovation is going to come on in this intersection between invention and insight of what is the market, how do we do it, who benefits. So a word of caution, though, since we're talking about Spain and in a European context, of not waiting too long. This is a very interesting chart which shows the percent of penetration, meaning how many people in a society, right, adopted a given technology and how long it took. So if we look at the automobile, it took 125 years to reach, say, 70–80% of a society. Okay, we look at the telephone, that curve, is getting a little bit steeper. Electricity, the VCR, radio, television, and then here we're looking at the internet, cellular, PC. So what's the message if I was a legislator or running a company anywhere? You would say, oh, I could be for the automobile, say 50 years late, and then I would join in, and I still had 80% of the market to go. Now you're 20 years late, you're done. You better catch the next one. So here, if you have the most advanced, for the case of Europe, if you have the wealthiest nations in the world investing heavily, putting their money where their mouth is, and they already have a lead technology on you, if then you say, well, I'm going to wait and figure it out, and I'm only going to do the smart ones. Once everything is figured out, have the killer application for me, it'll never work, right? So that's a little bit of this is a very important message to take home, I think. So it's occurring more rapidly, innovation. It requires open and a wider collaboration across disciplines and specialties. And this concept of intellectual property, I hope we have a chance to discuss it, because that's a very difficult model, and a lot of the IP, how it's being generated, and the patent system in the United States and other places is in disarray and very problematic of how we do innovation. So even a company like IBM that today has in the corporate world the biggest R&D sort of departments in the world. We have 8 research laboratories and over 3,000 scientists, and we spend over $5.5 billion a year in R&D. We never would ever think of doing this alone when we do this. So one of the things that has emerged across the industry is cost-sharing development alliance. You have to ally yourself with many other peoples in networks that work. So we are partners with Sony and Toshiba and AMD and Infineon and a lot of other partners, and we put very, very smart people together, and they have to be funded to get this to work. So never do things in isolation. If you're trying to talk about an industry, if you're saying, I want in Spain, I want it to be competitive in electronics, I'm going to just have my little people here, and they're going to do the thing. It'll never work like that. So you have to integrate yourself in alliances that work. That's a very, very important message. And there's plenty of examples. So when we do innovation, we should innovate about the way we innovate also. What systems we create. What's the right environment by which industry and academia can collaborate? Sometimes it's terrible the way they collaborate. One abuses the other, one short-sights the other. Sometimes it's very effective. So go around the world and explore what works and what doesn't work. Some people have better ideas than others. So in the 80s, there was Sematech, in the United States, which was a consortia when the semiconductor industry in the United States was getting killed. And it was very effective. By the early 90s, that was a consortia between government and the private sector, in which competitors engage in pre-competitive environment to develop technology together. And then they compete. And that was very successful. But now Sematech, maybe it's a little bit going down. And EMAC, say in Belgium, is doing very well. They have a different model, more a la carte. I'm interested in this technology. I just joined for this technology. I don't have to be like a full club member. So in Albany Nanotech, this is an example of like the state now pumping $2.5 billion in North State New York to do collaborations between industry, university, and government. So innovation is also occurring in this area. And figuring ways to do this, and in Europe there are examples, and in Asia there are examples, should be at least 50% of your discussion in general. If you're a legislator or you have a funding decisions to make is, yes, I'm interested in nanotech, but more importantly, how do I do this efficiently? How do I do R&D and commercialize R&D efficiently? You should spend at least 50% of your time thinking about that. Who's done it? How do I do it? And be effective there. So in conclusion, the market. Well, electronics, if you can intersect it, is an enormous market. I mean, it's a $1 trillion plus sector. The semiconductor industry alone is $200 billion. And it's sort of like the poster child of innovation. 40 years ago, it didn't exist, right? I mean, that's incredible. It has entered the nano era in the sense that it manufactures with nanometer control. A lot of people are aware that you have to control things to a nanometer. So it's useful and it's important, and there's lots of people who build tools for this industry that they can be used elsewhere with limitations. And there's plenty of examples also if it's different because it's nano. Say our gate oxide that we have in our transistors. We got to a certain point in which we had tunneling going through. It didn't work. Nano. We were having a different physical effect because we were scaled too down, and we had to innovate to solve that problem, and we come up with solutions to address this issue. The real reason that this label is exciting is because it allows us to work. The sciences and technology is nothing new. We can work together, and that's exciting on its own right, and put a lot of attention of how you innovate, how you collaborate, how you engage in cooperative competition regimes, right? So you don't only compete, you must cooperate to win. And how do you structure these partnerships? So that's all. Thank you.
Thank you. Excellent. Thank you very much. That's,
Do we have time for
Sure.
a question? I think that this was a very informative and interesting talks that you gave. The idea of a billion, 1,000 million transistors per square centimeter.
Yeah.
Now that's really enormous. 10 to the 9 things per centimeter square. It's interesting that in the brain, the number of brain cells per centimeter square is only 10 to the 7. Huh? Mm-hmm. So it's a factor of 100 more that you can put in a chip per centimeter than in the brain. But still we know that the brain is much smarter than the 1 centimeter square of a chip. So the key is that the number of connections per cell is 10 to the 4. Namely, there is 10 to the 11 synapses, and you take 10 to the 11 connections to 10 to the 7 cells, namely active devices of that, you get 10 to the 4. And in your case, each one of these transistors and so the elements is connecting only to a handful of cells.
Right.
And so innovative, I think, in this area will be truly to think how to bring connectivity with this 10 billion thing to a much higher level, and then you may actually be able to produce a thinking machine, something that will not make moral judgments, but it may actually be able to do a new brand of computing, namely not just taking current ways that we do computing and do it on more things per centimeter square, but a completely new thing that will revolutionize our ability to use computing as a predictive device.
Yeah, I understand what you're saying, and that's a good point. I think in between we have a shorter challenge. Now we have sort of supercomputers available on demand. And a big challenge we have is who uses them, right? How so what? I give Hank Smith, you have a supercomputer, and it says, and? You can use it. There's a very narrow...
Ask me, I'll tell you.
There's a very narrow set of people who can use it, and we have to find applications so that we can untap the power of what we've built. And I think that's sort of the next 15 years, 20 years, and then we can move on to making even smarter things.